Hi, it's Mr. Carson again, and this time we're looking at the atom. And many of us know the word isotope and know that it's simply an atom that's got a few extra or a few less neutrons than the normal atom. It might be radioactive or it might not. It just depends upon the atom itself. So we need to think about that because one of the biggest things we use in chemistry is the relative atomic mass, or RAM, and that depends upon the number of isotopes and the abundance and mass of each one. So let's see if we can work out how to use that to work out what the RAM is, or use the RAM to work out how much of particular isotopes we have. The basics boils down to the discovery of this wonderful thing called a mass spectrometer. Now, a mass spectrometer helps us understand the different forms of atoms or the different isotopes that exist of each particular element. And it also does the relative abundance of the elements. In other words, it tells us how many of each isotope there are. So when it comes out of a machine, what we actually do with the mass spectrometer, and you don't really have to know all these details, but it's nice to understand how it's done. We start off by pushing the atoms into a beam of electrons. Now, the beam of electrons, strangely, knocks electrons out of the atom, and usually it knocks one. So the atom now becomes a positively charged ion, and the charge on most of the ions is +1, which makes it very, very interesting for us to look at later when we see the chart. And it's the mass and a charge ratio that actually ends up telling us a bit about the atom, and that's on the chart anyway. So then what we do is we make the atom go through a vacuum. So we've sucked all the air out of this big tube, and we fire these atoms, make them into ions, and then use electric fields to accelerate them, make them go faster. Then we know that since they're charged, we can use magnetic fields to cause them to be deflected. So we put them through a variable magnetic field, and they hit the detector plate, and then that is transferred into an electric current, and that decides how big a peak you get on your detector. So it's pretty interesting little process, and we end up with something that looks like this. And this shows us simply all the different isotopes of a particular element. And we can see there are 1, 2, 3, 4, 5, 6, 7 in this case. Now, the height of those peaks tells us how many, right? So we have to remember that we need to add up to work out how many total we have. We need to have a look at, and if we had a scale on the left-hand side, the vertical scale, we would be able to work out the average of these masses of all these. Now, we can see that we would have to add the height of the peak at 92, 94, 95, 96, 97, 98 and 100 to actually get the total number of these. So we need this to think about this later on, because sometimes in your exam you might see this sort of a peak, this sort of a spectra given to you and say, right, tell me about it, and to use it to calculate the relative atomic mass of this particular element. So we can see that this goes on. Now, this tells us about the range, and I've got it here and I'll let you read this. And it's just what I've gone through with you. There are 7 isotopes. They range from 92 to 100. AMU stands for atomic mass units. If we're only talking about atoms, we talk about atomic mass. If we're talking about moles, we talk about grams. So please be mindful of that. So the units you should give me in a calculation of an isotope should be in atomic mass units. Now, it also says here the most abundant isotope occurs at 98, and this is a charge to mass ratio. So or mass to charge ratio. So if it's a mass of 98 and the charge is 1+, it's 98 AMU. And the total, as I said, is the sum of the heights of all of the peaks. So we have a look at all those. Now, here's an example of what you might be given. they've done a study on boron, and they said that 19.9% of was a boron 10 and had the atomic mass of that. Notice it's not a whole number. While 80% is at boron 11. So we would think that the atomic weight, or the RAM of boron, is going to be closer to 11 than 10. Agreed? So when we're calculating it, we simply do this. We simply look at the percentage and multiply it by the mass. As you can see, 19.9 over 100 times 10.013 plus 80.1 over 100 times 11.009. If we then do the sums in this, we see that we have these two, and we say that the RAM of boron is going to be 10.81 AMU. If we have more than two isotopes, we simply add that to it. We simply just add them to it. Same process, just add more of these sums to it, that's all. So if we look at it, that's what boron's atomic mass is. I've used weight in here as an old term. All right, now the alternative is they give us the atomic mass, or the RAM, and they then tell us about the fact that it's got two isotopes. And then we have to work out the abundance of each. Now this is a little bit trickier. So what we do, we can use A or X or whatever. I used A in this case to denote the abundance of lithium-6. Notice I only talk about the 3 at the bottom. Remember, with our conventions, the top number is referring to the mass, in other words, the number of protons and neutrons. The bottom number is referring to the atomic number, which is the total number of protons. And we can see that both isotopes have the same atomic number, but different mass number. So if the abundance of, or the amount or abundance of lithium-6 is A, then we know that the total will be 1, total amount of abundance will be 1, or 100%. So then surely the abundance of the 7 will be 1 minus A. Now the only trouble is we don't know what A is. So we plug those numbers into an equation down here below, and we see that A times the 6 plus 1 minus A times the 7 is going to equal the number we have, 6.94. And then if we go through the math, and then all I do is I put like terms together, right, and do subtractions. It's nice and simple, and we're going to see that we have a negative on both sides, which will cancel out, of course, and we find that we have, to find the value of A, we find this, and we find that A is 7.5%. So in other words, the abundance of lithium-6 is 7.5, which means the abundance of lithium-7 must be 92.5. Nice and easy. This is probably as hard as it gets for this sort of calculation, but you need to be able to do it. So keep that in mind.